And liftoff. Go Falcon, go MRV, and go MEP.
A Falcon 9 rocket soared into the sky over Florida's Space Coast. On board the 70-meter tall rocket, spacecraft that combined decades of effort from dozens of people across Northrop Grumman, the Defense Advanced Research Projects Agency, or DARPA, NASA, and the U.S. Naval Research Laboratory.
Oh, we are so excited.
That includes Bernie Kelm, the acting director of the Naval Center for Space Technology within the NRL. Spaceflight Now spoke exclusively with him in the lead-up to launch on July 21st.
So at the U.S. Naval Research Lab, our job is to look to the future and to see where the art of the possible will bring benefits to national security space and our national space capabilities. And I can remember when we were most commonly told, this is crazy. This is not how space works. What are we doing in this area? And would attack the technology problems and mature them and prove them out and show that we know how to do this. And with DARPA funding us at NRL, and we had a team that just kept working and working and going through the hard problems and got it to the point that the technology is mature and ready to go.
That technology is the heart of the spacecraft called the Mission Robotic Vehicle, or MRV for short. It's a public-private partnership and features the main payload, a pair of robotic arms dubbed the Robotic Servicing of Geosynchronous Satellites, RSGS for short.
In a robotic sense, we count a degree of freedom as a joint that can make one direction of motion. So the human arm actually has 7 degrees of freedom if you count them like a roboticist. Mm-hmm. You might think shoulder, elbow, wrist. You know, your elbow, if you're healthy, only goes one direction. Mm-hmm. Your wrist will have 3, and your shoulder will have 3. Mm. If you have a robot arm with 6 degrees of freedom, you could position your tool, so in my case, my hand, anywhere in your workspace with the attitude you want, you know, with some limitations. When you have that extra degree of freedom, I have multiple solutions that will get my hand to this. So I could move my elbow to different positions so that if there's an obstacle, like a thruster, mm-hmm. right where the one solution happened to be, I have more solutions. So that we can work on satellites that we did not conceive at the time we developed this mission. We don't know what our future customers are going to be. We don't know where all the obstacles are. So having a 7 degree of freedom robot arm gives us the flexibility to go to customers that we didn't anticipate. Having 2 robot arms lets us rendezvous and dock with one, and then do dexterous servicing opportunities with the other.
The concept for a purely robotic servicing solution goes back to the early 1990s, when folks at the Naval Research Lab began kicking around the concept. Kelm says over the more than 2 decades that he's been involved with this work, there have been plenty of naysayers.
Oh, we had many. We had that the moment we go and touch another satellite, it's going to float away. And so we built up a zero gravity test environment in 2 dimensions and rotation, and we proved it out. And that we can't carry enough compute power. You know, our spaceflight computers are much slower than what we have on Earth. We have to survive the radiation environment for a very long time. So we proved that we could do this on computers that we could fly, and that we could run the machine vision algorithms and the robotics control algorithms and everything and make it work together. We had a myth for a while that there would be, as soon as we got close to another satellite, there would be a lightning bolt of discharge and we'd both die. And at NRL, we have a plasma physics chamber, and we simulated the environment we would have at GEO. And we found the worst case, and we found that we know how to engineer a solution that will make it work. And so we just kept taking all of these problems, working with DARPA, engineering solutions, and getting this ready.
The way that the MRV works is it approaches a customer satellite and is then able to use one of the robotic arms to grapple onto it, and then use the other arm to either attach a mission extension pod, an MEP, to provide additional fuel and propulsion, or perform other servicing as needed. One of the more unique locations where early testing of this technology occurred included overnight work at the Smithsonian in Washington, D.C.
One of the things that we had never really quite known was how our relative navigation spaceflight cameras and spaceflight sensors would work against a very large, very fine mesh reflector. Some of these reflectors that spacecraft use as part of their antennas are almost invisible to the eye. They're such thin wires, we're like, how would we see them? And so I contacted the Smithsonian, I said, can we borrow some of your models and bring them to NRL? They said, no, we can't do that. And I said, can I bring a scientific team out and a couple $1 million of spaceflight hardware to the Smithsonian? And like, we would love that. And the Smithsonian team could not have been better. That we worked 5 p.m. to 5 a.m. for 2 consecutive nights, setting up approaches and fly-arounds around the TDRS model they had that was hanging directly over Space Shuttle. And we learned a lot. And then after that, we came back and we built a scale model in our lab and said, all right, now what if the satellite is in motion and there's relative motion between? And then we used the scale model to fill in data that we couldn't collect at the Smithsonian. But that was a team of about 20, and everybody had a grand time for two back-to-back nights.
Some of the other early critical groundwork towards this mission was laid by Northrop Grumman with the launches of their Mission Extension Vehicles 1 and 2 in 2019 and 2020 respectively. Dr. James Shoemaker, the program manager for DARPA's Tactical Technology Office, says this was one of the major milestones that made the MRV and EP mission launch possible.
Northrop and Space Logistics actually creating their own commercial sourcing industry, because it sort of proved that you could actually dock with an unprepared satellite on orbit and not break it. And so there's always a lot of concern with the clients on, can you actually do this safely? And they've, like, in taking the safety issue off the table was a big milestone that they did on their own. And now they're extending it with RSGS and MRV.
But as the technology questions got knocked down, there was still the matter of creating a business case for this type of service. Alongside the NRL and DARPA in studying the marketability of this type of robotic servicing was NASA.
When you work in a field like this, you struggle to understand why it isn't obvious to everyone else that we need to have this in space. But we do have this kind of cultural tendency to just do things the way we always have, and the way we've always done things in space was once you launch them, you never see or touch them again. And of course, they all have to fit into a single launch fairing, right? So imagine if we did everything on Earth that way, where anything you built had to fit in the shipping container. You couldn't have 2 shipping containers. And then anything that you deployed also had to be, perfect out of the box with no opportunity for repair. And so, like, I think, to me, when you phrase it that way, it's obvious that this is, why are we not doing this in space? It's the only place we aren't. So yeah, I hope we'd be here 10 years ago. It's been a long struggle, and part of it's a technical struggle, but a lot of it also is a cultural struggle to convince the world that this is, feasible, viable, actually beneficial to do work this way.
Say in the 20 years I've been working on this and doing technology development, the business case problem is just as hard as the rocket science. And with Northrop Grumman, I'm thrilled that they found a solution where, with their mission extension pods that the MRV, RSGS will install, they have something that they can schedule. They will know when people need more propulsion. And so that's a schedulable business case, and they can make plans. A lot of the other really high value of the mission is anomaly resolution. We never know when there's going to be the next anomaly in space, but when there is, we could potentially be saving billions of dollars of spacecraft with this mission.
The MRV and MEPs sitting inside this payload fairing ahead of launch already have their destination set. They will service satellites from Luxembourg-based SES and Australia-based Optus, as well as customers who weren't publicly disclosed as of publication. As to where things go from here,
From DARPA's perspective, actually, we're probably pretty much done.
It's the end of the road for you guys.
It's the end of the road. Our job is to prevent technology surprise, take the technical risk off the table. Once we prove it can be done and transition it to someone else, then we have to move on to something new. And you can see even there's a fair number of other commercial companies starting to get interested in servicing and working on it on their own. So there's less need for DARPA to invest in it to keep the technology going.
As for future applications, NASA's Bo Naz says the MRV technology opens up new possibilities for satellites in geosynchronous space.
If you're building very big satellites, you have some competition. This is maybe a way to add flexibility and upgradeability to make it more competitive, and I think that's absolutely true here. You know, I think the payload is a third at most of the mass of a spacecraft. And so if you want to put a new payload in space, you don't have to launch a whole spacecraft. You just have to launch a payload and install it on an existing platform. And I think there's a lot of capability there that makes bigger spacecraft much more competitive than they used to be.
And regarding the MRV MEP mission itself, it'll take about a year for it to reach GEO and begin its servicing journey. The MRV has a 10-year mission out ahead of it, and only part of it is relatively set in stone. Kelm says this could be the potential for a new future in geosynchronous Earth orbit and elsewhere.
I hope we see this as a real inflection point in how we do space. You know, we, the team, DARPA, NRL, Northrop Grumman, with our support from NASA, are servicing clients that aren't designed to be serviced, because that's what's up there now. As users and customers of space get more comfortable with satellite servicing, and we see this as a routine, reliable capability, if we have future satellites designed to be serviced, the level of services and level of capabilities will just become exponentially greater. Look at the USB port on the computer and how many more things that is doing than anybody ever figured was what it would be intended for. If we have USB ports in space, we can much more easily install batteries, sensors, computers, all types of upgrades as satellites start to be designed so that servicing can come in and help them out.
Reporting for Spaceflight Now, I'm Will Robinson Smith.